All right, starting chapter 7 on differential equations. Today we're going to look specifically at modeling situations with differential equations. So one situation that can be modeled with differential equations is population growth. Our equation would have a variable t for time. That would be our independent variable. And then p, the number of individuals in the population, which is our dependent variable. An equation for the growth in the population would be dp over dt is equal to k times p. Basically means the change in population with respect to time is equal to some constant times the population. So what we would want to do is find a solution to that differential equation. So the problem, in this case, asks us to find an equation whose derivative is a constant multiple of itself. We do know a function that when we take its derivative, we get that function back exactly as it was, maybe times a constant. That is our exponential function. So if p prime of t, or dp over dt, is equal to some constant times in parentheses ke to the kt, we can rewrite that as k times in parentheses ce to the kt, where ce to the kt is actually equal to p of t. So we have a constant times the population function. Because populations are always positive, our constant c has to be greater than 0. The initial population when t equals 0 would be c. You can find that by plugging 0 in for t. And the last thing is no population is going to grow in a strictly exponential manner. Eventually, population levels off. So we can do some things to modify our equation to take care of that. So we would want to consider two possibilities. Initially, the derivative of population with respect to time is going to equal some constant times p, or roughly equal that, if p is small. So initially, population growth is exponential. Then the change in population with respect to time is negative if our population is ever greater than some value k. We call k the carrying capacity, the maximum population that an environment can support. In other words, the population decreases when the population exceeds the carrying capacity, or the maximum. So we can write that as dp over dt equals k times p, our initial exponential function, times 1 minus p divided by k. So as if p ever gets larger than k, then 1 minus pk is a negative, giving us a negative growth rate. In other words, a decline in the population. So some general information about differential equations. A differential equation is an equation that contains an unknown function and one or more of its derivatives. The order of a differential equation is the highest derivative that occurs in the equation. most of the time we're going to be looking at first order differential equations, but today in our initial look, we will have some first and second degree differential equations. So here might be a typical problem. Show that every member of the family of the function y equals 1 plus ce to the t divided by 1 minus ce to the t is a solution of the differential equation y prime equals 0.5 times the quantity y squared plus 1, minus 1, sorry, minus 1. To show that, the first thing we're going to do is find y prime, find the derivative. So y prime, we've got a uh, rational function with t as its variable. We're going to have to use uh, the quotient rule. So great thing about differential equations, we get to review derivatives. The quotient rule says take the denominator times the derivative of the numerator. And the derivative of the numerator would be the derivative of 1, which is 0, plus the derivative of ce to the t. Well, c is just a constant. Derivative of e to the t is e to the t. Minus the denominator times the derivative of the numerator. Derivative of 1 plus, uh, sorry, the numerator times the derivative of the denominator. 1 plus ce to the t times the derivative of 1 minus ce to the t. Derivative of 1, again, 0. Derivative of negative ce to the t is negative c e to the t, all over the denominator squared. And we are going to simplify this a little bit. If I distribute, I would get c e to the t minus, let's see, c times c is c squared. E to the t times e to the t is e to the 2t minus, we have negative ce to the t times 1, so minus a negative becomes plus ce to the t. Excuse me. And then we have minus ce to the t times minus ce to the t, which is again going to be positive c squared e to the 2t all over 1 minus c e to the t squared, which I forgot the square in the original. Right, denominator squared. If I combine my like terms, I have ce to the t plus ce to the t, that's 2 c e to the t. I have minus c squared e to the t plus c squared e to the 2t. They cancel over 1 minus ce to the t squared. Perfect. I'm going to leave it just like that. Next, I'm going to simplify what was on the right side of my equation, 1 half y squared minus 1. So if I go back and look at what y was equal to, y was 1 plus ce to the t over 1 minus ce to the t. So I'm going to have 0.5 times 1 plus ce to the t over 1 minus ce to the t squared minus 1. I'm going to write that 1/2, 0.5 as 1/2, as write it as a fraction. Uh, 1 plus c e to the t over 1 minus c e to the t squared is 1 plus c e to the t squared over 1 minus c e to the t squared, minus 1. So I would really like to um, simplify that fraction. So I'm going to find common denominator. So my first fraction is going to stay exactly the way it is. And my common denominator is 1 minus c e to the t squared. So 1 is going to become 1 minus c e to the t squared over 1 minus c e to the t squared. I am not going to do anything to the denominator. I'm going to leave it as 1 minus c e to the t squared. One of the reasons, if I go back real quick, that's what my original denominator looked like. So keeping it that way makes the process a little bit easier. I do want to simplify my numerator. So if I multiply this out, I would get 1 squared plus 2 times the product. So that would be 2 times 1 times c e to the t. So that would be 2c e to the t plus c squared e to the 2t. And then I'm going to subtract 1 squared, which is 1, minus 2c e to the t plus c squared e to the 2t. That's just using the binomial theorem to expand that expression. I'm going to change the subtraction to addition and change all of my signs in that second fraction and combine my like terms. So I have 1 plus negative 1. They cancel out. I have 2c e to the t plus 2c e to the t, which would give me 4c e to the t. And I have c squared e to the 2t plus negative c squared e to the 2t. Those cancel out. All over 1 minus c e to the t squared. Last thing I'm going to do, I'm going to reduce this 2 and this 4 cancel, leaving me with a 2 in the numerator. So I end up with 2c e to the t over 1 minus c e to the t squared, which is exactly what I had for y prime. So I've shown that y prime equals 1/2 times y squared minus 1. Thus, that original equation is a solution of that differential equation. What would really be nice is if we could figure out a value for c. In order to do that, we would need to know some initial condition. So, what if we had an initial condition that said y of 0 is equal to 2? So we know that y equals 1 plus c e to the t over 1 minus c e to the t is a solution. So if I plug 0 in for t and set it equal to 0, or set it equal to 2, I can solve for c. E to the 0 is 1. If I multiply both sides by 1 minus c e to the 0, I get 2 times the quantity 1 minus c e to the 0 equals 1 plus c e to the 0. Then I use the fact that e to the 0 is 1, so I get 2 minus 2c equals 1 plus c. Solving for c, I subtract 1 from both sides, add 2c to both sides. I get 1 equals 3c, or c equals 1/3. So I could plug 1/3 in to both of my uh, values for c. Relatively short assignment, problems 1, 2, and 5. Enjoy your weekend. I will see you on Tuesday. If you have questions, don't be afraid to email me. Uh, I also will have office hours from 12:15 to 1:45.